To welcome Professor Edward Guinan. He agreed to be one of the IC colloquial speakers for this year. Professor Guinan is a professor at professor of astronomy and astrophysics at Villanova University since 1969. He obtained his PhD. Well, actually, he got a position before he obtained his PhD, as I'm going to say. He obtained his PhD in astronomy at the University of Pennsylvania in 1970 and has been working on variable stars and eclipsing binary systems for more than 35 years. From his research, Professor Guinan has gained great expertise in all physical phenomena related to a wide range of wavelengths of the electromagnetic spectrum, from X-rays to the infrared. More recently, Professor Guinan's interests are focused on the impact that active stars may have on their hosted planets, which is the topic of his presentation today. And he is also interested very recently on the artificial network, neuronal artificial network techniques for studying and analyzing huge data sets. Professor Guinan's research on variable stars, solar-type stars, exoplanets, and binary systems has led to his election as a president of the International Astronomical Union Commission 42. This is closed binary systems, and also president of the IAU Division V. This is variable and binary stars. He is also reviewer, he's also advisor and peer reviewer to the NASA space program. In addition, Professor Guinan is co-chair of the International Astronomical Union program on teaching astronomy in developing countries. As a consequence, he has organized astronomy schools in countries like Morocco, Iran, Nepal, the Philippines, Colombia, Vietnam, and a few more countries that I don't remember right now. Professor Guinan is very prolific. He has published more than 600 papers, as you can see from the ADS, and his work is very well recognized by the community with nearly 3,000 citations. So we thank you very much for coming and visit us.
Well, thank you very much for. I'm supposed to stand over here. Thank you very much for having me. I enjoyed my stay and meeting people here. It's a very vigorous institute. So I've had a nice time talking to a lot of people, and I still will continue. I would like to see the sun on the Canary Islands, but fortunately, by mistake, I had an umbrella in my suitcase from my trip to Paris, where it always rains. So I'm glad I did not remove it. I've been using it every day here. So I'm going to be talking on the effects of the star has, the magnetic activity of star has on the hosted planets. And this is we'll get to this in the middle of the talk. I've been doing a project called Sun in Time. And this, first of all, my living with a red dwarf. As you know, always, you have to give things titles, so we decided to call this Living with a Red Dwarf, but it can mean other things. But it's a study of these red dwarf stars. They're very common. 75% of the stars in the sky are red dwarfs, these little guys. They live forever, and their X-rays and ultraviolet radiation is only from the magnetic fields they produce. I have collaborators up there. One of them is actually Spanish. We would like to be called Catalan. Ignacy Rivas. And so we work with astrobiologists, planetary modelers, because my background is in stellar dynamo, stellar work, magnetism. My expertise is not in planets as much. I can't model a planet atmosphere. So we have a group of, and then undergraduate students. These are talking points. I'll get through the first part. Will be fast. I'm going to talk about the Sun and Time program, a program we started, 1980s, 85. This is to study the sun by using analogs. Stars that are like the sun, G2, but in young clusters and intermediate age clusters to map the whole evolution of the sun out. And that program is still continuing, but almost finished, because we have been observing this, doing these observations for 20 years, and I'm going to show you the results of that, and then go into the new program, which is this red dwarf stuff. So they're living with the red dwarf, talking about those stars, and then you get into the magnetic fields. Let's see if I can do two things at the same time, maybe. Yes. So this is a little bit about M dwarfs, about dynamos, and then here is the astrobiological consequences of the XUV radiation, which is significant, and then highlight a couple of these red dwarfs that have been detected to have planets. There's actually no concerted efforts to find planets in red dwarfs until recently, but 22 have been found without trying. Now there's programs to search for planets, and they're finding them, and they're finding the planets are actually small planets, as you kind of would expect. Planets like the Earth, super-Earths they're called. And then a little bit on the future and so on. So we're going to go through the sun, just a quick review of the sun since you're a solar physicist here. The sun is it's a G2 star. It's old, 4.5 billion years old. It spins 25 days. Its magnetic activity is very diminished from what it used to be, but it still causes us problems. Blowouts of satellites when there's flares. It affects our climate, things like that. And the sun really has an 11-year cycle. It has Maunder minima. The sun is still not understood. The dynamo of the sun is still not. They cannot produce the 11-year cycle unless you play a lot of games with the sun. So the sun is our nearest star, but still there's problems with understanding it. That isn't going to be this talk. So magnetic sun, everybody knows. You see all these phenomena. You see the in different wavelength regions. This is actually from here, from La Palma. This is granulation, sunspots. Magnetic field in here is about 2,000 Gauss, and out here a bunch lower. Here's a flare. You see the loop structures, and then you can see a picture taken from one of the satellites in the X-ray region. So the sun is extremely active. Actually, it's very quiet right now. The sun is at the minimum of its cycle. It just started its new cycle. A couple spots have been seen. And you have effects like, no, I'm pressing the wrong one. One of the things you do see is during the interaction is the solar-terrestrial relationships. And this is the sun. We're not that close, fortunately. If we were this close, we would have major problems. But some of the stars around the M dwarfs are actually that close, some of the planets. But what happens is that what will turn out to be the thing that I learned and didn't know when I started this program is how important this is, how important that magnetic field we have around the Earth and around other planets that don't have magnetic fields have problems, and maybe have, if they had life, they don't have life now. Even for us, with the sun now, without this magnetic field, there would be problems for us. In the past, we're going to get into this, when the sun was young, it emitted 10,000 times stronger X-rays, 26, 27 big flares a day. And without this protective field, it would have destroyed, or actually would have eroded the Earth's atmosphere, as it did to Mercury, as it did also to Mars, when Mars lost its magnetic field. So one of the things we have here is things like aurora. You see these kind of things. And there are relationships. This is solar terrestrial. It's hot. This is a weather. It's called solar weather. It used to be called solar terrestrial relationships. And these things have effects on our climate to some extent. They cause the ionosphere to, even today, the sun affects our ionosphere, causing it to heat up 1,000 degrees, puff up during the solar maximum. Actually almost destroyed Hubble Space Telescope 10 years ago, when, if it wasn't a mission, the drag of the ionosphere was causing the satellite to fall in. And sun and time, I'm sorry I couldn't do much more with changing. It's always 3 o'clock in this program. So A little bit more time, I could have had that move. I could have set it to be this, but too much trouble. So this is the program. We use solar proxies. The Sun and Time program is comprehensive. It studies X-rays all the way out, actually, to the radio region. So it covers all these bands. It's hard to know all these bands, too. I mean, it stretches my mind. Radio is much different than X-ray when you start to do the analysis. So I have collaborators who work in some of these regions. I don't know the radio region very well, but I do know the others. So what you do here is use proxies. These are analogs. And we select single stars. The Sun is a G2 star. And so we select stars that are within 3 or 4% of the mass of the Sun. So that's what a G0 is, slightly more massive. A G5 is slightly less massive. And one of the most important things is to have the same structure. The magnetic field of the Sun is generated by its convective zone, convective envelope, which goes in about 25% of the way. And it's the rotation, the convection, and the shearing that takes place that produces the Sun's magnetic field. So we wanted to have stars that were matched. So matched in mass, matched in internal structure, differing only in age. And age is the clue, age and rotation, because the Sun has spun down. The Sun used to spin much faster in its past. So what we need to do to complete the program is to find, in the beginning we needed bright stars because this program began 20 years ago. And the satellites, Hubble was not around at that point while we were starting, but we used satellites like IUE, small satellites. And so they had to be relatively nearby to get the X-rays and to get the ultraviolet data. No rotation periods. We got the rotation periods from simple photometry. The young stars have spots, big spots. They have 10% light variations. The Sun only has 1/100% light variation with its spots. So they actually vary, and they vary easily, 5%, 10% light variations, the young ones. Sometimes we have to use, for the older ones, we have to use calcium H and K to map the chromospheric, to use the chromosphere as a marker. So the rotation period is important because it's a two-pronged project. One part of the project is actually, you'll see down here, is to study the dynamo. The other came about later on was to create irradiance tables to see how the Sun's X-rays and ultraviolet evolved with time, because you can't do that. There's no way to model that by theory. You can model the nuclear, but you can't model the magneto-dynamical part of the Sun. So that's why I use analogs. In fact, even some of the things we find are not explained, the heating that takes place for the present Sun. So well-determined distances. Hipparchus made a big difference. We had problems before Hipparchus with parallaxes. And even some of these nearby stars, the parallaxes were off by 10, 20%. Hipparchus saved us because our X-ray luminosities that we were using were all now could be correct to a few percent. So that little satellite with parallaxes was a big plus for us. Age is important. Age is hard to get. So ages for the young stars is pretty easy because you can go into clusters like Pleiades, Hyades, things like that, or even very young ones, pre-main sequence. You're in Hans's field. Then you have a lot of star-forming regions. But I actually don't deal with that so much because planets don't form yet. They're forming. I deal with the ZAM's Sun, the Sun when it reached the main sequence, when it had blown away the gas. So I deal with that time rather than go back to pre-main sequence. We do have pre-main sequence data, but things are a mess back then in terms of what you do. And so in here then, the moving groups are very important. These are stars that are moving. You identify their membership because they're moving the same as the Hyades, say, but they're near us, and the Hyades are far away. So this was a godsend to identify nearby bright stars. There's many of them, like Sirius is one. Very nearby bright star that can be identified to be a member of a cluster, Hyades moving group, or Ursa Majoris moving group, and you can get ages. When you get into older ones, first of all, you would say, why don't I use evolution tracks? Evolution tracks are worthless for young stars. And once they get to the main sequence, they're all the same. We can't distinguish. I change the temperature by 20 degrees K. The age changes by 1 billion years. So it's not very good. Older ones, yes. When they get to be the Sun's age and older, they have evolved enough that you can determine ages, like Alpha Centauri. nearby, great parallax, you can get its age, 5.8 billion years. Or you can do its seismological age, which is a little bit younger. Actually, I believe the evolutionary age. And so some of the older stars, we get evolution. And then we've made relationships between period and rotation, and I'll get to that. We recently, and that's what this talk is about, we recently added the K stars and the M stars. These are cooler. So this was this started as a laboratory because we had a star exactly like the sun, and it's like you take it into a laboratory and you spin it up and see what happens. And so what comes out? How does the corona change? Does it have a cycle? Does it have, what's its heating mechanisms? So that was the original. It was a dynamo experiment that went wrong. Actually, it went right because then I realized that the X-rays and all these things changed so much, and people who were modeling planets like the Earth, early Earth and Mars, actually had screwed up. And they were using the wrong things. They were scaling things wrong, and they were using... they were making guesses at what the early sun was like. And so this is when I started to combine the two into planets, the evolution of the Earth and the planets, Mars, and the dynamo part. So, and actually, the funding helped when I added the planets to the program. Observational data goes all the way from X-rays to radio. Why high energy is important is because of photoionization. The X-rays photoionize, the ultraviolet photodissociates, so it causes chemical reactions in the atmosphere. This is the result. I'll just show a few results. This is a plot of X-ray luminosity. This is 10 to the 30th ergs. This is age in giga years, should be GA. Here's the sun, and these are a sample of, there's 28 to 30 stars here. I only showed some, but there's many, many young stars up in here. This is the zero-age main sequence sun. This is a Pleiad star, so it's 100 million years old. You see a rapid decline about 1,000 times from the youngest to the sun, and it continues to fall, but in a way that these stars actually have cycles that you have to worry about the activity cycle where you're catching it. The sun varies a factor of 5 from peak to trough during its 11-year cycle in X-rays. So you need multi-samples to get these right. So I don't know whether we caught that at a minimum or what. This is a very old star. And here is rotation in days. It should actually be plotted 1 over p because it's really frequency, but 10 days, 20 days, 30, 40. And this is age again. And again, you see the sun is 25 days, and then you start with 2 days or so, half a day. The young stars all over the place, a half a day to 3 days, because it depends how fast they were born, whether they have planets and disk connections. But when they get to, it doesn't matter how they begin. If they begin with a half-day period or a 3-day period, by the time they get to the Hyades, which is right there, they're all the same. They're 7 to 8 days. That's what the Hyades rotation rate is for a G2 star. For the Pleiades, they're everywhere. They're half a day, 2 days, 3 days. So what happens, the young stars spin fast, have strong dynamos, and they spin down faster. They lose their angular momentum through magnetic fields threaded in their winds, as the sun is actually doing today. So it's a self-compensating mechanism that it's no longer fun for me. I mean, if you tell me the spin period of a G2 star, I can tell you, unless it's a binary, I can tell you the age. So it used to be fun, but now, I got tired of it. So I moved on to different kinds of stars. So this is what we've done, and this is the irradiance tables are too hard to plot because you can't plot all this in. I went too fast there, but this is X-ray, the youngest star, which is Pleiades. These are the ages of. I just put 4 or 5 in this diagram because it gets very crowded. But you see an X-ray between the youngest and the sun. This is about what the sun is. It's 10,000 times in the hard X-ray. So this shows you the decline. These are all plotted as irradiances. This means the flux at 1 AU. Of course, if you have a different planet, you can change that, but I put them all at 1 AU. So here's the oldest, like the sun, and here's the young. You see the decline. This is EUV, the youngest with these strong lines. And again, you can hardly see these because I kept them on the same scale. The emission goes way down. And the FUV, just taking a piece, the youngest, this is coming from 500,000 degree plasmas. called the transition region between the chromosphere and the corona of the star. And again, a big decrease with age. And far ultraviolet, same thing. The youngest star, the oldest star. The bottom one is like the sun. Of course, if you were just plotting this, you would change the scale and you would see these lines, but I don't. So putting all that together, we made a smooth plot of the spectral irradiance normalized to the present sun, so it's 1. So in X-rays, the young sun had 1,000 times. The ultraviolet soft EUV was about 100-time decline, and the FUV was 20-time decrease. And then they continue to trail off, but they asymptote. They kind of become more or less level out here. Like the sun, when it's 8 billion years, will be about half the X-ray luminosity that it has today. So the decline has curve leveled off. This shows you the other thing. This is the nuclear evolution of the sun. And this is pretty easy. The sun, when it was a young star, was cooler, smaller slightly, and its luminosity was 70% of what it is today. So the sun has been getting warmer, and as time goes on. Now, if you plot this over here, it's going to do this, because the sun becomes a red giant. But it's slowly, in fact, the end of the Earth occurs about here. The sun will be about 10% more luminous. It causes evaporation of the oceans. It causes a runaway greenhouse effect, and the eventual loss of the water of our planet ensues in about 1 billion years. You don't have to wait for the red giant phase. We have problems. We could have problems from our own making before that, but the sun is on a course where it will cause the Earth to be too hot. The Earth is in the inner part of the habitable zone right now. Venus is not in the habitable zone. So it's on the intersection of it, and there's no way to go. There's no way to save it because the water is going to evaporate, and that makes the greenhouse effect. But there is a problem that people like to talk about. It's called the dim sun paradox, that the sun was dim in the past. How come the Earth didn't freeze over? That's another paper in itself. So the faint sun, or the dim, sounds like a Chinese breakfast, dim sun. The faint sun paradox, easier to say. So people worry about that when you actually put the sun at 70% of what it is today, the Earth would freeze over with its present greenhouse constituents. The greenhouse effect on the Earth today is about 33 degrees. So it's good. We have greenhouse gases because we would have frozen over. The oceans would freeze and albedo would go up. But it's enough to keep us above the freezing point. In the past, when you take the same Earth atmosphere and you reduce the sun by 30%, the Earth does freeze over. So there's a big controversy of what happened. And it's pretty easy to resolve. Carl Sagan was one of the first people to mention this, that the early Earth had more greenhouse gases. Not maybe more, but different kinds. Methane is a very, very strong greenhouse gas, 20 times stronger per molecule than CO2. So methane, even a 0.25% is enough to cause the Earth not to freeze over. So that's a whole other area, and I just mentioned it in case you didn't know about it. The sun was fainter, but in X-rays and all that, it was tens, hundreds, thousands of times stronger. So to summarize the young sun, strong X-rays, this is the sun near ZAMS, up to 1,000 times. The visible light was 70%, so the sun would be dimmer. So, and actually you would see spots too. You'd be able to resolve big spots covering the surface. In the far ultraviolet, 5 to 80 times. Solar wind, I don't have time to get into this, but the solar wind has been studied by Brian Wood by using like our heliopause. They're stars that have astrospheres, and where the wind of the star interacts with the interstellar medium, and he's able to infer what the winds were. The winds of the young stars were maybe 500 to 1,000 times stronger. Very important number to know, but still uncertain. It means when you add and how much flaring, the flares were 10 to the 33 to 10 to the 35. Presently, a good flare is 10 to the 32 ergs, and you get like 15. We did a month of monitoring flares on young stars and found their flare rates just to see what you need that data when you're going to do the modeling. And the young sun may have been a little bit more massive, 2%. It may have lost about 2% of its mass. So what we're going to do now is the effects of this on the solar system. And so the sun has coronal mass ejections, it has flares, it has winds, and things like that, which you'll start to experience in a few years, and when the sun comes out of minimum, and the interactions with the magnetospheres of the planets that have magnetospheres anyway. And so we'll get to now what happens. This is a paper that I started working with astrobiologists in 2003, 2002. Helmut Lammer, this is his student Griesmeyer. We gave them our data prior to publication, and they started to model everything. Every planet, everything. So this is what their conclusion was, is that if the planet did not have a magnetosphere, it had a hydrodynamical blowout from the early sun. That is, the X-ray and ultraviolet radiation caused photodissociation, ion pickup, and the winds swept the atmosphere away. And that effective temperature of the planet was not the important quantity here. It was the temperature of the ionosphere, but whether a planet lost or kept an atmosphere. So this is a picture of a planet, one of these exoplanets that are hot Jupiter type things that is relatively near. What's happening with it is that it's losing like a comet tail, and actually this has been observed. One of these planets actually goes in front of a star, and you can see the material in here. So this blowing off. So this is the ion pickup mechanism, is that you have the wind, you have the X-rays and all that coming in, and what happens is that these ions are picked off the atmosphere, ionosphere of the planet, and swept out into the solar system. If it's a planet that doesn't have an atmosphere like Mercury, it happens right on the surface, like the potassium. Mercury has potassium and sodium that even the sun today can pick up. It's like a photoelectric effect in a way. The X-rays and ultraviolet from the sun cause these ions to be released, and then they get swept off by the wind of the sun. So Mercury today is undergoing small erosion, but the sun is very weak. So this is the first one. This paper is a strange one because I don't necessarily believe the outcome, but because to have this work, they made so many assumptions. They assumed Mercury was the same size as the Earth, and this is like 4.5 billion years ago, 4.3, and it's hard to know even if Mercury was there. So you get into like a lot of problems with the early solar system. But if you take an Earth, you put it where Mercury is, and then you zap it, you let the sun, you look up those irradiance tables, and you start to irradiate, and you cause it to tidally lock, which means it turns off the magnetic field. This is what can happen. So this is Mercury today. Mercury today is undergoing erosion, but it's very small. There's potassium and calcium and silicon ions that have been detected in the solar wind blowing by, picking up. It's the nearest planet, so it gets the most damage. It's the nearest to the sun. Mercury looks like, the moon on the surface, but it is nowhere near the moon. It is a very unusual planet. It's called the iron planet. Here's the size scale to scale the Earth and Mercury, but now I scaled them up to be the same size. You see this giant core, has a large iron core, so they call this the iron planet. And because of that core. When you plot it on a graph of diameter versus it doesn't fit. Even the moon fits here in these terrestrial planets. Mercury's way off for its size. Now, why? There's several reasons. It was captured. It had collisions. One, the reason that I'll talk about very briefly, is that the sun got it. The sun blew away not just the atmosphere, but took out the mantle. Down to making the mantle was lost, making the core of the planet be about 2/3 of the way out to the surface. Again, to have this work, we need winds that are 2,000 times the present winds, and the data suggests that it's only 1,000 times. Also, you have to have Mercury there, formed at 4.5 billion years. It had to be in the position it's in today and things like that. So this is the process. The sun, you put in the numbers, which are hard to see, but what you have is a blow-off taking place. erosion. It's called ion pickup or sputtering. It's a common process. Meteorites have this going on the Earth, the surfaces, the sputtering process. So you have the atmosphere blowing away. Venus is harder, and I don't even have time to talk about Venus because I never get to the red dwarfs. But we have a paper out on, this is a radar map of Venus. Venus has a very thick atmosphere. Today it's carbon dioxide, volcanic origin. But it once had water, probably, because the deuterium to hydrogen in its atmosphere indicates the presence of past water. And the reason this works is the deuterium is heavier, so that ratio tells you something about can give you something about the evaporation rates of hydrogen versus deuterium. And so if you go back, you can kind of get an idea that early on, Venus had an ocean, but very early on. And because what happened is in the early days is that this process, its far ultraviolet radiation will dissociate water. This will dissociate into oxygen and hydrogen, and it all got blown off. And you do the modeling, it happens in the first 0.2 or 0.3 of a billion years. So it goes away very rapidly because Venus, again, we had Venus's magnetosphere turned off. If Venus was rotating, it probably could have saved some of the water, but it looks like it maybe, we don't know what it was doing 4 billion years ago. So this is where you make your assumptions. It's the planetary. So, so it may have had water, but the water is all gone. And that's the paper they used our data on. It's a 55-page paper, so it's a very detailed paper with lots of math. I'm leaving the math out of all these talks because you don't need that right now. Earth is actually very hard to actually model also, but there's more known. So the early Earth, we assume the atmosphere, which was a reducing atmosphere, was methane, nitrogen, no oxygen, carbon dioxide, and a 1 bar to 2 bar atmosphere. But this is the radiation coming in. The Lyman alpha is the strongest. Hydrogen Lyman alpha at 1216 is actually very important. And that actually causes ionization. It causes the ionosphere to be puffed out to be 8,000 degrees. It can go up to 7,000 to 8,000 degrees, the ionosphere, from the heating when the sun was young. Today it's just 2,000 degrees. Enhanced solar wind, and you have all the X-rays coming in. So what happens in this model, and this again is a whole talk on its own. So I'll never get to the red dwarfs, so I'm not going to go as long as Hans. So I'll try. So one of the reactions that takes place, some of the reactions that takes place is in the early Earth, is that you can destroy, methane is a very fragile molecule. In fact, that's the proof of life on Earth, is that it's destroyed in about 100 years. If methane were not replenished, the present ultraviolet radiation of the sun and the oxygen would destroy it. So it's proof that the Earth has life, is to have methane and oxygen. You can have methane. If you don't have oxygen, it's okay. So one of the things is that you have to worry about the young suns. What happened to this? Why didn't it get destroyed? Carl Sagan, before he died, had a paper out why it didn't get destroyed, is that they had the Earth enshrouded by dust, the collisions that the Earth was undergoing in the first 500 million years. It's called the age of bombardment. Asteroids, comets hitting, made a dust cloud, that kind of a shield, like a ring, that kind of shielded the Earth. They also could get it from volcanic activity, that the aerosols block the solar radiation from getting in. This is how they try to explain how the methane didn't get completely destroyed and the Earth didn't freeze out. The other reactions are formation of ozone from water, because there's no oxygen yet. Oxygen doesn't come for 2 billion years, so the early Earth had no oxygen. But what happens is that there is oxygen from water photoassociation, briefly. One of the things that happens is one out of millions of chemical reactions which you can fill pages with. Most of them aren't very interesting, and they're very complicated, and they interact. But one of them is kind of neat. It's the photoionization can form this carcinogenic molecule, formaldehyde. Formaldehyde, for the older people in the audience, is a preservative. They used to put little frogs and things like that in and you would have a biology lab. And I worked with that stuff, and it smells like alcohol, kind of, but it is a carcinogenic element, so it's been banned. You can't use this as a preservative. But, so formaldehyde sounds bad, and actually it is bad, but it's one of the building blocks of life. So this reaction here that breaks carbon dioxide up into carbon monoxide can lead to, with these reactions, can lead to formaldehyde, this element here. And this is one of the key building blocks of ribose, key ingredients of life. So it gives just a taste of what can happen and how these ultraviolet radiations are good and bad. In this case, good, maybe, producing a more complex molecule. And of course, life. It's Halloween, so 3.5 or 3.8 billion years ago, life began on Earth. So things had to settle down enough. Probably began on Earth 4 billion years ago, but probably got wiped out. A big solar flare, an asteroid hit, a comet hit, sterilized the Earth. So there are probably many times when the Earth tried to have life. But 3.8, 3.7 billion years ago, it happened, and it's been constant. Well, it's been evolving, but we've had life since that time. Mars. This paper on Mars is actually probably the strongest one of the group, where the data was taken. Try to explain Mars today. Mars is a desert, cold planet, has a very thin atmosphere, 9 millibars, so it's 1/90th the density of our own. Nitrogen, carbon dioxide, little bit of water, and but there's evidence on Mars of canyons and riverbeds and things like that. So this evidence is overwhelming today that Mars had water. It's overwhelming. There's no question about it anymore. There used to be 3 or 4 years ago. Phoenix scraped the surface, found ice, and so there's no question. But in the old days, and this is years ago, you had these features here look like they're produced by running water, and they are. And the conclusive result is this one, which was this object was found, but kept secret. It's a water slide. I don't know if you have water slides in Spain, but this is and of life. But this is Mars attacks. So this is the story. This is the story on Mars. Mars was a happy, wet planet 4 billion years ago. It had an atmosphere of maybe 1 bar, like our own, had water, possibly had life. Possibly had life. So this is Mars, 3.5 billion. And why? Mars is a small planet. It's further from the sun than us, so it receives about half the amount of radiation, which is okay. It's going to be colder. But greenhouse effect gases in the old days would make it warmer. And the water on Mars was, in fact, if you compute it, was 50 to 100 meters, the ocean, if you level it all over Mars. What happened? Well, in the early days, Mars has an iron core, as you know. It's a terrestrial planet, but a small planet, 1/10 the mass of our own. So in the beginning, it had an iron core and a magnetic field, liquid iron core. It rotates, liquid iron core, and produced a nice magnetosphere. So the sun was doing bad things, but most of the winds were going around here. Some were coming into the poles. So it was more or less protected from the mean sun, from the sun when it was young. The core, because it's a small planet, the core froze out. And there's very good evidence for this, about 3.5 billion years ago, or 1 billion years after Mars formed. When that happened, it left Mars exposed to a weaker sun. This is the sun 1 billion years old, a Hyades age star we use as our sample for that time, 3.8 billion years ago. We use the Hyades for G-stars to compute the numbers here. So what happened is that, Mars, I think this is a separate slide. I'm going crazy. So what happens in here is that Mars, 3.5 billion years ago, when the field went, you started to leak away. The ionosphere puffed up, photoionization took place, photodissociation took place, water got broken up, but and the greenhouse effect diminished. Mars was wet and warm, but most of it was due to water. And so it blew off the hydrogen. It doesn't go off as 2 H's, it goes off as 1. So it blew off the hydrogen, but oxygen being heavier didn't diffuse out. It only lost 1/8 as much. So it lost some oxygen, Most of the oxygen is there in the soil. So the model shows that the oxygen on Mars is still there in the iron ferric oxide rocks, the red, what makes the planet red. So, and that can be tested. How much, if you can dig in there and see how deep the regolith is and see how much oxygen there is, you can actually go back and compute the ocean levels. Some of that stuff is going to be meteorites. You have to be careful. Some of it might be original. But that's one of the checks of the model. Now, why Mars didn't lose all of its water? And that's what happened is that it froze out, fortunately. Mars got colder and colder as over 1 billion years to the point where the water sublimated. So it meant that it didn't lose everything because it got too cold. The greenhouse effect diminished. Mars became a cold planet. The water was left behind. I mean, something like 10% or 20% of the original water should still be there as ice and permafrost and things like that. And it might be. That's what the experiments. In fact, one of the satellites shows that Mars has a lot of water underneath. A proton experiment. They shoot X-rays, microwaves down, find that. You had a question.
Was that due to the cooling off in the core just by losing heat?
Losing heat. Both. That's what happens on Earth. Earth is cooling but slow. It's losing heat, and it's a much smaller core than Earth. So it's a capacity, the heat capacity of the planet losing and less radioactive. A gig a year, and it's there's proof for this now. You can go back and figure out the time. Mars has little fields left, frozen fields, but not Martian. The Martian magnetic field is 1 over 100,000 the Earth. So it's from a frozen field. This is confirmed. When we did this, it was not confirmed, but this has been calculated. And now, in my last, I can get through this. This is the Red Dwarf program. So we had the Sun in Time that got grants because of the planets, actually. I mean, what saved us? No one cared about the dynamo. I don't know. That was my reason for starting that program, was to study the dynamo and heating and all the exciting physics. And I did that stuff. But when we started to add, when exoplanets were discovered, this rejuvenated that program. We started to have in the title, studying, the title used to be The Sun in Time, a Study of the Solar Dynamo. And then when that kind of maybe it got funding, maybe it didn't get satellite time, but we added and effects on the Earth and life and planets, it was funded. And this one is another thing. It's a logo. I was thinking, it takes a couple bottles of wine and I'm going backwards. Let's go forward. It takes a couple bottles of wine to come up with a good Spanish wine. It can be cheap, actually, to come up with a name. So we call this Living with a Red Dwarf. And this was the logo. This is our site. So when you write proposals, you have this in there, and people can visit it, and you put some papers in there. The original logo was this one. That's Snow White and the 7 Red Dwarfs. That was not so good. So that has been dropped. That wasn't a good choice. That was too much wine. So for basics of M-stars, since people do M-stars here, I talk to people who do these little stars. They're low-mass stars. Their masses are half the Sun, down to 0.7, so they are cool. Their luminosities are low, 1/20th to 1 over 1,000,000 for the very faint ones. But their lifetimes are forever. They live, some of these stars they never die. They just live forever. Trillions of years, because of nuclear evolution. Their nuclear fusion rates are extremely low. They have low masses, but they are burning their fuel at such low rates. They're called stellar misers. They keep their fuels. But 75%, it might even be 80% of all the stars in the solar neighborhood are M-stars. For dynamo questions, they have deep convective zones. They're very deep. In fact, at a mass of 0.3, they're fully convective. So they're interesting to study compared to the Sun. And they now have been theorized to have super-Earths, which is turning out to be true. So a paper in 2005 predicted because of their... First of all, we got nothing for this with planets until a paper came out. We had no funding, nothing, until, because no planets have been found around these, until a paper came out by Alan Boss, who did a modeling of the... Because they said planets wouldn't exist around these stars, that their accretion disks were too thin, too small. Alan Boss came out with a theoretical paper that showed that planets can form, do form, and they're smaller planets. They tend to form Neptune and lower size planets. And then they started to be discovered. And so then we started to have some success in getting time on X-ray satellites. No one wants to do, there's people here who do X-ray binaries. I mean, these M stars are very low luminosity. Their luminosities are 10 to the 28th or something like that. That's good. You can't compete with a black hole with 10 to the 35. So when they're on panels, when they're up against black holes with black hole X-ray binaries, their energies are way, way down. So the people who are energy biased. And so you have to have a good argument. And we were arguing dynamo, deep dynamo, what that does, and also what happens to planets that are hosted. Right now, my student, former student, did a study of the Sloan, and he has identified over 30 million DM stars. It's a lot of stars. And he has 340 million photometric objects, and he has spectra over for 1 million of them. 50,000 are M dwarfs. So it's a big breakthrough. So with the Sloan. This is just a quick comparison. Here's the Sun. This is a DM0, a DM5, and a DM8. This is a borderline between a star and a brown dwarf. You start calling these T's and things like that when you get out into there. So this guy has 1/10 of a solar mass, and this has about 1/2 a solar mass. So this is the scale. And this is the numbers. You see M stars are way up. So the stars within 10 parsecs of the Sun, you have a 75%. And it's a sample. They keep finding, it's actually 242 now. I didn't want to change the slide. They keep finding a few more of these with surveys. This is the energy, how they're distributed, and they peak. It seems to be M4 or so, seems to be the peak, and then they fall off. And maybe the brown dwarfs come up here, but this is what they found. This is over 30 million stars are used here, so it's pretty strong. I always believed that these kept going when I was in graduate school, that people believed that these got more and more, because they didn't see the turnover, but the turnover is definitely there. How they look inside, this is the scale, Sun, M star. This is Proxima Centauri, the nearest one, but they're fully convective. They're convective zones, the Sun goes down 25%. These go fully. So they have kind of a different kind of dynamo than the Sun does, although they have behaviors that are like the Sun. So there's some question about the dynamo in the Sun is this section in here, shearing section. These stars have similar behavior in spot cycles and things like that, that I question some of the conclusions that people have on our dynamo model. This is a picture of a very active M star where these magnetic fields were actually measured using spectropolarimeters. So they do have magnetic fields that are measurable. This is a diagram showing stellar evolution, age, log luminosity. This is an F star. It lives a very short time, becomes a red giant. This is the Sun. We're here. So in the future, it becomes a red giant. And here's a K star, and here's an M star. The change from there to there is 0.5%. So I could draw this diagram out here forever. I can, actually, and it would be no change, 1% change in 20 billion years. But they're going to do the same. That's how you compute habitable zones. If you want to compute the temperature of a planet, you can do it using this. One of the ways is using this equation. It depends on the albedo of the planet, the luminosity of the star, how far away you are, and when greenhouse, the big question mark in all this is greenhouse effect. So, but this equation works for a rapidly rotating planet. It is bolometric. It's more complex than this. But for the Earth, when you put in an albedo of 0.3 and you put in a greenhouse effect of 31, you get what the Earth's temperature, average temperature is using this equation. And albedo is, some people are doing albedo studies here. And Enrique Enriquez, there he is. So it's very important quantity. This has all been normalized. So you can compute habitable zones using that equation if you wish. And it tells you the habitable zone where you can have liquid water under a kind of Earth-like greenhouse effects of 30 to 50 degrees, not Venus. Venus is like 400-degree greenhouse, but these are the habitable zones for the sun. The Earth, this is 0.9 is the inner. Earth is here. And then you could have an Earth-like planet, even 2 AU out. If you move Venus 2 astronomical units out, it's happy. That greenhouse effect, that would be very good. So they're kind of broad because it depends on the albedo. It doesn't depend, and it depends on the star, of course, but the albedo of the planet is the big, and the greenhouse effect is the big width here. K-stars, notice you're in close. This little dotted circle is called the equivalent Earth. That's where you would have Earth-like conditions for an Earth-like planet. So around the K-star, to have the same conditions, you would want to be half an astronomical unit. And for an M-star, I can't even show you how. For an M-star, to have that Earth equivalent zone is 0.1 AU. So for an M-star, you have to get close to the star to stay warm. So you have to move in. He's just a little fire, right, just to keep warm. For a G-star, you can stay far away. I don't bother with F-stars because they don't live long enough, probably, for life. 2 billion years is not probably enough. But for an F-star, it's 4 AU. You have to, and B-star, forget it. If you're a planet around a B-star, it's not, you don't have time to do anything. And you are 10 AU away. So these are rough calculations. They're called habitable zones. I'll skip that. These are the M stars that have planets now. There's actually one more. And these are the Gleason numbers. This is the spectral types, the Vmax. Notice they're all close because they have to be detected. This one has 3 planets. So you see B and C and D. And these things that you see, ME is Earth masses. These are Jupiter masses. So this guy's like Neptune. This is like Saturn. But notice these guys here are important. These are super Earths. These are planets 5 times, 7 times, 10 times the mass of the Earth, about double the diameter. And they have been detected. This one here in blue is new. In fact, this is a very important one because it transits. Its inclination brings us, so it cuts in front of the star, producing a transit eclipse, which is very, very useful in determining all the properties. There are 2 more on this list. I didn't update it because I'm not positive they're planets for reasons that M-stars have spots, and the spots produce motion in the radial velocities. It can produce motions. Uneven distribution of spots can mimic a radial velocity variation of a planet. And some people have been burned already with this. They have found planets, and then they have taken the planets back because it was due to the star's rotation. So that list is available on our website. Let's see. So what's interesting then is, so far, and it's a small sample because there's only 22 planets around M-stars, 1/3 of the 20 known planets with masses less than 1/10 of Jupiter are around M-stars. So not a surprise because the disk is smaller. In contrast, 3 of the 280 known Jupiter-sized planets orbit M-stars. So there's a tendency for smaller planets around M-stars, but that's not a surprise anymore. And Boss's work is being borne out. That's just a picture of one of the systems. GJ876 is a DM star, not drawn to scale because you see here this is a kind of a Saturn-Jupiter thing. So you find things and you just stick them in there. You make up these things and you steal from other. I think that's Neptune. We use all these satellites. This is for the Sun and Time program. This is for this program. Rosat, Osca, XMM, Chandra. This is to get the corona. And we actually, in the Sun and Time program, we could actually use Rosat. But now, and these were alive. The only ones alive now are this. This actually had some problems a week ago. But we have active programs. So we use archival data. Archival people who observed the M-star just for the hell of it. Or it was in the old sky survey. So the other data is, this satellite is dead, so you have to just take what people did. IUE has something like 1,000 spectra on M stars. So we use that archival data. Fuse is just dead. We had a program on that to do the FUV. We got 8 stars in before it died, and HST's living. No, it isn't living well. It's in hibernation. I don't know what you would call it. These opticals, these are robotic telescopes that we do the spots of the M stars. We're just following the same program as the solar stars. This is a small telescope at our university for training students. We have students observe these things. This is a robotic telescope at Kitt Peak. It's robotized. They were closing down the telescopes, and they gave this telescope away. But we had to spend $1 million to refurbish it. It was a mistake. It would be better to destroy that telescope and buy a new one. You live and learn. That was the 50-inch telescope at Kitt Peak. Some people old enough have used it. And these are our robotic telescopes that cannot be used by humans. There's no place for an eye anymore. And these are we had the first robotic telescopes, actually, in 1980s. 1983, we had a robotic telescope before anybody else. They weren't much, but they save you a lot of time in sleeping. You can sleep. If you have an anniversary with a wife, she doesn't appreciate it if you're out observing on anniversaries. What you get, this is a quick comparison. This is a comparison of an M star. Actually, it's Proxima Centauri is this guy, and this is Alpha Centauri A. So in the far ultraviolet, Proxima actually has more flux. But then you get to the near ultraviolet, the continuum of the G star cuts in, and it overwhelms Proxima. So Proxima Centauri's 11th magnitude, and in the optical, and Alpha Centauri is 0. So you can see the big difference. But in X-rays, they're the same. X-rays, Alpha Centauri and Proxima Centauri, same amount. Another showing, again, a comparison of what happens in the whole ultraviolet spectrum. An M star, a K star, and a G star, all very young. So when they're young, the M stars and K stars have about the same fluxes. But again, what happens is that the continuum cuts in, overwhelms. This is a irradiance diagram for an M star. And the major, this is the continuum. We didn't do spectra out there. We should. And these are the lines that are most important. X-rays, and then the Lyman alpha and Lyman beta are the strongest lines. In fact, we spent all this time modeling and getting the data together and making lines. We had 3 angstrom resolution. The modelers took that data and integrated it from 1 angstrom to 1,500 angstroms, and they called it the EUV, and that's what they used. I was not happy because I spent so much time calibrating, but that's all they care about. And what really matters is are these 2 lines here in terms of ionospheric physics, the Lyman alpha and Lyman beta. And I was a surprise to me because those lines are contaminated by the Earth, and we had to do a lot of work to take the Earth effects and interstellar effects out for them. What happens with ultraviolet radiation is that it can affect, if it gets through, it can affect the DNA. So here's a UV photon. It screws around with DNA, and then you have some problems. I won't get into that. As the astrobiological sections, what it does. The thing you remember is FUV radiation does not get in. Anything below 2,000 angstroms or 200 nanometers does not get into the Earth's surface or any planet's surface. It even has a thin atmosphere. Mars doesn't get. Beyond the NUV radiation penetrates. It depends on the type of atmosphere. So FUV, no problem for the people on the surface or things on the surface, but it does have a problem with disintegrating or eroding away the atmosphere. Beyond that, long-wave radiation, NUV, can penetrate, and then we have our ozone protecting us, oxygen and water protecting us. So that's what the DNA damage happens. Below about 300 nanometers or 3,000 angstroms, it's serious if that gets in. It can cause DNA damage. It can cause skin cancer, which it's doing us now because of our reduced stratospheric ozone. So what we've done here is to calibrate this is Alpha Centauri. This is spots. Alpha Centauri is a DM star. We have, it has a spot cycle of 6.9 years. This is 1 year. This scattering here is because of rotation. These are rotations of some of these M stars. They just scatter because it's taken with a small telescope. We have better, we're getting periods of 86 days. The rotation period is very slow. But they still have spots. This star here has a nice spot on its surface. And they spin down fast because they're small and the magnetic fields are very strong. So the M stars, we have periods 200 days we've tracked, and they're still active. And this is a nice one too. This has a really nice, well-defined light curve in the V band. That's with our robotic telescope. And the bottom line here is that we have light curves or rotations. These are really rotations for 60 of these stars, and we have ages for about 20 of these stars. So now we have age-rotation relation for M stars. So that means if you tell me the rotation or tell me their X-ray, I can tell you how old that M star is. And the trouble is we have trouble with old M stars because we can't, they're members of old clusters, they're too faint to get. So Proxima Centauri is our sun for this sample because Proxima Centauri's association with Alpha Centauri gives its age. So and when you look at spots, what we're getting is that we think they're heavily spotted like this, and you see slightly more spots on one side of the star, maybe if that animal turned around. This is a strange cow. It's called the North American cow, the world cow they call that. But what you have is that when you model spots by light curves, you are modeling a differential effect, more on one side than the other. You have to have Doppler imaging, or you have to use other techniques. We use other techniques to actually get how much spots they have. But for right now, we think they're all heavily spotted. We're getting the variations due to maybe 2 or 3% differences on spots on one side of the star than the other side of the star. And I won't get into that. So this is the same kind of diagram you saw before for G stars. This is LX versus age. These are our stars that have pretty well determined ages and good LXs. Again, you see the decrease in coronal emission with time, similar to what happens with solar stars, but it actually happens faster. So we have this for ultraviolet. We have this for far ultraviolet. We have irradiances. This is the near ultraviolet. These decreases again. This is far ultraviolet. So we are creating these irradiance tables to use for M stars, planets around M stars. Moving groups, they're hard. Moving groups, Hyades, Pleiades are easy, and then association with another star is how we get the ages. We can't even get to the M67 with great, but we can't. The rotation periods, that's 4 billion year cluster, 4 billion year old cluster. Be great to get to that, but they're 20th magnitude, and the period would be 120 days. The variation would be 1%. So who's going to give 3 months or 4 months of time to monitor that? I mean, all you would do is take one picture a night, one CCD image a night, but you'd have to have it over months to see the variations. That would be a significant thing. So right now, space motions, high velocity. Kapteyn star is a population 2 star. So it's got to be 10 billion, 11, 12 billion years old. It's moving 300 kilometers per second. So that's how. We're stuck with the older stars. And I'll zip through. Who cares about? They flare. You have to worry about flares for a brief time, for 5 minutes. An M star can become an A star. That's not good for life. This shows a flare detected, and it went up 10 to the 4th time of what it was pre-flare in the near ultraviolet. So dangerous. You have to live close to this planet, to the star, and these stars can turn into an A star, like have 10,000 degree plasma and far ultraviolet briefly. This is another flare. Flares become important. So what the bottom line turns out to be is that we can get ages. I want to talk about this last system. This is just an example of a system that contains 3 planets. It's called GJ 581. A is the star. Here's the sun to scale. These are the periods of the orbital periods, and actually they're probably the rotation periods of the planets. 5 days, 1383. These are their masses. These are their radii, and this is to scale. This is the planetary system. This is the habitable zone, computed. This planet C, which is a super-Earth, is located on the inner edge. This is too hot. This might be too cold. And this is the range of temperatures that you get. In America, we use the Fahrenheit scale, but it would be not bad, not bad. 15 to 75 degrees C. Depends on what you do with albedos and greenhouses effects and things like that. This planet, though, is tidally locked because this star is 6 billion years old. So this planet we don't know, no one's seen this yet, but it is by theory should rotate like our moon. One side should always face the star. So the rotation period should be equal to the orbital period. This is the orbit is 0.07. So it should be tidally locked. So one side should face the sun, the star. The other side should be in darkness. Now, that was bad news. If the planet doesn't have much atmosphere, papers in 1990 said this is the end. What would happen is that the atmosphere of the planet would condense out on the cold side, leaving it uninhabitable. This would be a desert. This would be ice, and goodbye any hope. With a 1/10 of a bar atmosphere or higher, circulation takes place, like it does on Earth. The equator and poles exchange air. So a paper by this paper, Joshi et al., Icarus, 1997, a follow-up paper, 2005, shows that you would have it's not this simple of a circulation pattern, but actually you can maintain an ocean. You can have heat coming from this side of the planet, making its way over to the cold side, and the cold air sliding in and heating up like we do with the Earth. So in the Earth, this would be the equator, and this would be the pole. But for this planet, it would be continuously facing. And that looks bad, and it's good. I mean, that could be, what's good about this is that there's some bad things. This 13 days is kind of long for a dynamo. So this planet may not have a strong dynamo, a magnetosphere. But if it's a super-Earth, 5 times, it might have a larger iron core and a strong dynamo. Even though it's rotating slower, it could compensate and protect the planet from its atmosphere being blown off when the star was younger. So super-Earths look good. In fact, I'd rather live on a super-Earth if I was near an M star than an ordinary like our own Earth. But I'm not sure what life you would have here. I mean, they would live on the dark side, I imagine, and get their energy from the other side or try to live here. I don't know what would happen in those. But it doesn't rule out life. And when you have 75% of all stars being M stars, you might have, even though the chances aren't as high, just 10% or 1% gives you very high numbers of possibilities for life. And so this is a close-up of what could happen. These are the numbers you get for these conditions, for the star, for the distance, for the albedo, and for 1 bar atmosphere and for less. So these are numbers you get. They're not unreasonable numbers. In fact, it would be kind of nice today to have the temperature to be 36. Not 36. 36 would be nice today. Not bad for beach. Now, what kind of life would you have there? Well, in a super-Earth, that planet you would have 2.5 times, so it would have to be kind of like a hawk. Pretty strong legs to walk around. be hot and dry, and because you would have 2.5 times the gravity. So strong legs would help. And this is more on by Frank Celsius on habitable planets around that star. So this is the paper that discusses it. M stars you have to worry about. You can't use bolometric when you're doing the irradiances and transmission. Actually, the infrared gets trapped. You have an inverse greenhouse effect. You get heating from the infrared. We don't get that. We get heating from infrared leaving. But M stars are strong in infrared. Conclusions. 75% of all the stars are M stars. So you're going to have some of these, and they live for a long time. The DM0 stars, 40 billion years. The DM5 stars for 200 billion years. 300, you get into forever, as long. So there's no changes. Greatly, if these stars are found to be habitable, if you can show that there's planets and that's happening, they increase greatly the percentage of finding life in the universe. Also, they have been found to have super-Earths already. There's 2 programs, one in Texas, one in the south. Also, they're now targeting M stars for planets. This star has this C, possibly could be habitable. It depends on the greenhouse effect. D, which is further out, could actually be habitable too if it had a 100-degree greenhouse effect, like 100 degrees, something like Venus. So, and it would still be synchronized. The other conclusion is they haven't been thoroughly searched yet. So when and now SETI and things like that are targeting these stars. They used to throw them out. Well, they weren't easy. I mean, it's easy to get a G star because they're 6th, 7th, 8th magnitude. M stars are 9th, 10th, 11th, 12th. So you have to have a bigger telescope to get the kind of spectra you need, because you need to measure meter per second precision. So it isn't until recently that big telescopes like Keck's and your telescope became available, where you can do meter, 2 meter precision on a 12th or 11th magnitude star. M stars have lots of lines to allow the measurements. And more interesting is you have to worry about this tidal locking. I mean, is that good or bad? I don't know. Could be good, it could be bad. It could shield the life form on the dark side from the star. It could actually cause the atmosphere to collapse. And it could slow down the planet where it has no magnetic field, leaving it vulnerable to lose all of its atmosphere. And finally, the interesting thing is that half of the M stars in the solar neighborhood are older than our sun. So here we have a chance to find civilizations, if they could exist, if they could get through the early days when the M stars were flaring and had lots of X-rays, that could be 1, 2, 3, 5 billion years ahead of us. And UFOs, and maybe some people here are from an M-star civilization. And so you get into these SETI programs where now we're sending radio signals to some of the nearby M-stars and searching for radio signals from nearby M-stars. Proxima Centauri does not appear to have a planet, so that seems to be ruled out. That's the nearest one. Wolf 359 might have a planet. It's 3 parsecs from us. So they're interesting. Wolf is 7 billion years old, Wolf 359. People who watch Star Trek, any Star Trek people? Well, she'll know what Wolf 359 is. It's where a major battle took place in 22-something-60, where the Borg attacked the Earth and the Federation lost all its ships. I had that in a grant in a tiny, tiny print, and I'm a Trek person, so in a tiny, tiny print, and it almost got me the time. They said, maybe we should do Wolf 359. It has its own web page for Trek people. They know everything about that star. But most of the audience here is too young to know Star Trek. But it actually influenced me a lot. I chose that star because it was Wolf 359, not for science reasons. Then I said, it's good for science. So there's some crazy. So they're interesting for SETI, and now I'm end. And here it is. Perhaps there are many Earths to be discovered. This is they're not all going to look like that. And what our study shows, finally, is that M stars can be suitable hosts for planets with life. Not necessarily intelligent life, who knows, but life, as long as they're protected by strong or thick atmosphere and have magnetic fields. So what we have here is different types of, I made up these things. And we have these are the aliens that you don't want to deal with. these are the nice guys, and she'll know Spock, of course. But these are the ones you don't want to be visiting the Earth. And I wanted to thank you. And I have not seen that yet, but only on slides. Oh, is it clear? Oh, okay.
Okay, so there's time for questions, comments, suggestions.
Eduardo, yeah.
A few years ago, it was perhaps more popular to invoke more mass loss in the sun to account for the dim sum.
I know where you're going. Yeah.
But today you gave this number of 2%, and I would like to know more where it comes from, this 2%.
It comes from the mass loss. It comes from Brian Wood's study of Lyman alpha, the astrosphere. He computed the mass loss of the young sun, the rate, and it was about 1,000 times the present. And he integrated along the life of the sun. And he came up with the sun lost about 2%. It lost most of that in the first 500 million years. What he's getting to is something important. It is the dim sun paradox. 2%, 1.02. The luminosity of a star is a function of the third power of that number, mass. So it makes the sun 8% stronger. So people, if you can bring that up, the early sun, if you can make the early sun 1.1 times more massive, it takes out the young sun is not less luminous than today. So these people, there is a group of people who believe that the sun, you explain the dim sun paradox, the fact that the earth didn't freeze over, by the fact that the early sun was more massive and lost a lot of mass. I don't believe it, but that's a group of people who do. And that's where you're getting. That 1.02 makes, I think it's 1.02. It's shaky. I mean, the data on young stars for winds is very shaky. They're getting conflicting results because the magnetic fields, it may lose the mass through the poles. And the geometry is different. The dynamo is extremely strong. I mean, in terms of the planet studies, we don't know whether the winds are coming out of the poles and they don't affect the planets, or whether they are coming out of the equator. So there's a lot of uncertainties when you start to model the data on the paleo sun or the young sun in terms of the planet data. Not on the irradiance. I'm solid on that. But on the winds, they're hard to measure. ALMA is capable of measuring the winds of young solar-type stars and nailing it. Lyman alpha is the feature they use. And it's the astrosphere. It's our heliopause you look through, and you look through their heliopause. You look through the interstellar medium, and it's a tiny effect, and they pull out M dot. They pull out the mass loss. It's Brian Wood, B. Wood, 2002, 2007, 2005. He's a collaborator. He's if you're interested in that topic, I had to leave it out. You notice how long. I mean, I had to cut that out, and I knew there would be questions on that topic. But he's the wind person. You can't measure winds. It's very hard. The winds are, hard to measure. They're not like B stars where they're easy. Is that where you're? Yeah.
Continuing with the paradox.
Can't hear you. Oh. I'll keep back. I'm not allowed to. I have to stay here because they're taping, and I'm not in the tape most of the time.
Yeah. So you say the solution to the faint sun paradox was to add more greenhouse gases. But I was under the impression that only adding CO2 would not work.
It wasn't CO2.
CH4.
It had to be CH4.
But you mentioned...
Okay, the reason he said this is that there's geological evidence that there wasn't enough CO2 in the early atmosphere. So you have to it wasn't CO2 as people believed. It had to be CH4. Is that where you're...
What I did not know is, according to your ionization, that the lifetime of CH4 would be about 100 years.
Yes.
So you mentioned this...
That's today, yeah.
So it would be shorter in the past.
Yes.
There would be more irradiance.
But there's more of it.
Yeah. But a lifetime of 100 years is very short, and you mentioned this mechanism of protecting it with some dust. But dust in the atmosphere has a lifetime of...
Not in the atmosphere, it's in the stratosphere.
But even when you have
from collisions. Earth, the first 500 million years are really difficult when we model. The Earth and the planets are being bombarded.
Yes.
First, the moon collides, the moon forms from a collision. It's crazy back then. So...
But even if you put it in the stratosphere, the lifetime, when Krakatoa went...
Oh, it's not, the lifetime...
1 or 2 years, right?
No, 10 to 50 years, but it's multiple hits. The Earth's being hit many, many times.
And even if it lasted for long enough, it would defeat the purpose because your albedo would go up, so you would cool.
Yes. Well, it's a paper in 1995 by Sagan and somebody else, and just go shielding. It's called... Earth shielding or methane shielding, ultraviolet shielding. It's in. If you click on Carl Sagan, it's one of his last papers. It's Greenspoon is the first author. Check it out. I mean, there's one in 2003, one in 2005 about this mechanism. The other one is aerosols from volcanic. Early Earth was very volcanic. So the aerosols, you'd have to produce a lot of aerosols and shoot them into the stratosphere. The Earth's stratosphere was actually different then because it had no ozone.
They have a cooling effect.
Yes.
We have a volcano, the Earth gets cooler.
Yes, I know. You have to have a lot of methane.
And the last short question,
yes.
You mentioned that the evidence for early water on Venus was due to...
It's a shaky piece of evidence. It's from deuterium to hydrogen ratios from the fly-in, from 2 probes.
Okay.
And it's shaky, I think, not so definitive, but it's been recently measured and it's confirmed that it is. Yeah, they have a paper out a year ago, or half a year ago, from the Venus probe that is still claiming 50-meter oceans for depth of oceans. There's no geological evidence because it's been wiped out. I mean, you don't see, like you do on Mars, flowing water evidence. But what happened on why the CO2 didn't go away? Did you ask why does Venus have a thick atmosphere? CO2 doesn't interact with the sun. I mean, Venus's ionosphere is cold. The surface is 700 degrees and 500 degrees. The ionosphere is 200 degrees. So it kind of puts a cap because the ultraviolet radiation does not affect CO2 at all. It is hydrogen. That's what makes our ionosphere warm, is it has hydrogen where Lyman alpha stimulates it. Venus is cool ionosphere and traps. And the CO2 has no place to go. It has completely saturated the soil. So once you form it, it's stuck there. And this has been there. It could be replenished, but you don't need to. And there's no water, there's no life. So it has interacted with the soil, like we have weathering. Venus is weathered out. There's no place to put the CO2 except to stay into the atmosphere. It's an interesting planet. It's a very difficult planet to model. There's 2 papers on it, and this one paper is 50 pages long. And the best I could do is correct the English of parts of it because I didn't understand. I'm being truthful. I sent them my data, and I go, I hope they're not crazy. That they're doing this. I followed some of the equations, but I couldn't follow it all. But it's an interesting paper. It's too much, though. 50 pages is too much to read. The abstract is 2 pages. So I kept saying, cut, make it shorter. No one's going to read. Yes.
I have a question about the M dwarf.
M dwarfs.
You discussed many parameters for
yes.
M dwarfs, but you didn't touch upon the binary nature of M dwarfs. And is it?
These are all single M dwarfs.
I know.
Ones. Yeah.
And in fact, it seems that
30% are binaries.
Less binary frequency than G dwarfs.
But for good reason. Weaker gravity fields. Partly. Yeah, I do binary stars, but in these studies I eliminate. If I find a binary star, it's gone. Because it screws up everything.
You made the case for M dwarfs as being a good host.
No, let me go back on that. If I could take my choice, I would take a K star. Because K stars live a long time too. You don't have to be right on top of the star, undergoing flares, and you could be half an AU away. You wouldn't be tidally locked, and you would have a long life and prosper. So if I had my choice, K star, and we do K stars, but I took the extreme. See, we were doing G stars. We were doing K. They're very similar to G stars. So hey, let's go and do the M's, because if we do them, we'll get the extreme. And that's what I did. The other thing, for people who do M stars, my relationships, or these relationships with rotation age, fail at M6, M7. Those stars do not follow the same law. I question whether full convection is really at M3, because I see no difference there in any of our data between an M1 star and an M5 star. They all follow the same law. They all march to the same
Maybe
drum.
M6.
M6, the game is over. M7, they don't spin down. They are... Edward, do you know? I mean, we don't have enough in our sample. We don't... Different They behave more like a planet than a star. The dynamo, the winds, maybe the winds aren't there to make them spin down. They're different. We can't get that deep in our programs. We go to about 13th or 14th. We use small telescopes. I mean, we're not as lucky as the Spanish are. In terms of America, the evidence is in space. So stellar astronomy is not very good in the U.S. It's a dying field of sorts. Cosmology and things like that, and planet. So I'm still a stellar astronomer, but I'm staying alive because I'm doing planets a little bit. Got into exobiology. But it's a funny, I look in the Astrophysical Journal, the astronaut, I have to go to A&A to find stellar papers because there's very little published in the U.S. on stellar astrophysics.
Is the Sahu paper published?
Yes.
It is?
Yes.
You
No, he has not published it. I think most of his planets are false alarms.
Because this is Space Telescope
Yes.
data, so the stellar data. And so,
Published.
Can you summarize what he has found?
Well, he looked into the center of the galaxy and with the bulge, and found little transit-like eclipses for about 25, mostly M and K stars. Little signature, about a 1% drop. These are 25th magnitude stars, which is hard to do. That's pretty good. And what happened is that most of those turned out, because he's in the bulge, to be blends. There's a binary, eclipsing binary, one of the stars I love, contaminating the signal. So the eclipsing binary is 1 magnitude fainter, 2 magnitudes fainter, giving you a little dip. But the dip is due to the light dilution. And in 50% of the Ogle stars, same thing. They had to take back their planet detections. All but a few turned out to be planets. This is going to be a major problem for Kepler, a big problem for Kepler, because their resolution is 6 arc seconds. Every star they look at is going to have 10 other stars fainter in the field. And we have a relationship with Kepler in that we have an artificial intelligence-based program that can distinguish a true planetary eclipse from a stellar eclipse, 90 percentile. So they are in trouble. Corot also has this problem, not as bad, but they have it. They have not talked about it, but they have found a lot of blends. Is there somebody here from Corot? I discovered it when I was on the panel. I do binary work. I was on the Kepler, and I kept saying, you're going to get these W Ursa Major stars are going to be in your fields all the time. And eventually someone listened, and they shifted it out of the Milky Way. But Kepler can see a big field, but their resolution is 5 arc seconds, which is pretty big. So they're not clean measurements. Of course, follow-ups, you do spectra, and then, but spectra of 500 stars, they want to, what we're giving them is a ranked list. And we hope the artificial intelligence works. We don't know. Artificial intelligence is crazy. You don't know what it's doing sometimes. Sometimes it says, go home, Yes?
Okay, I have a naive question.
Oh, they're usually good ones.
How solar-like is the magnetic activity of the sun?
How what?
Solar-like.
How solar-like?
Like is the magnetic activity of the sun. I said, how do you compare the sun
to other
stars?
Good question, because we have found a solar twin. We found after searching, this was like searching for the true cross. We found a star that is matched in age, in mass. It's called 18 Scorpio. It's found by a Brazilian group. And that star we call it the night sun. And we got space telescope time, we got X-ray time. It is exactly the same as the sun. So the sun seems to be normal among other, that's what you're asking, is the sun normal for its age and for its spectral type and in terms of magnetic activity? And the answer is yes.
But for some years ago...
But if you look 300 years ago, I would say no, because the Maunder minimum...
No, but I speak in...
Okay.
But for some years ago, some people have observed flares in solar-like stars at the same age of the sun, more or less?
No, I don't believe it. Well, who did? Well, I mean, if you...
By Ravenstein and other people.
No, I've never seen it. I've never seen it.
And they say that these solar-like stars have stronger flares than the sun.
Yes, what they're doing is that the people in this field call solar twin, okay? A solar star. Well, this is the problem. Any star that's G2, they say solar-like. But they don't distinguish age. G2 young, G2 old, they say they're all solar.
They claim that they were of the same age that the sun, more or less.
Don't believe. I don't know what it... I've never seen... The place to go for that would be the M67 cluster. None of that's the same age as the sun, 4 to 5 billion years. None of those stars have ever flared, and there's 30 or 40 of them. I mean, I'd like to... If you could find... I'd love to see that because I don't know about it, and I am dubious. You have to be careful of solar stars in binary systems because it makes stars young. If you want to be young and active, you belong to a binary. And then what happens, well, it's like married, I don't know. And I don't want to go there. But I mean, what happens is that these stars synchronize. As they lose angular momentum, they get close and they spin up. So they behave very much like a young solar star, but they're gaining their energy from the orbital angular momentum loss as they move in and synchronize. So a lot of these are called RS-CVN stars. And a lot of those stars flare, are like the sun, but they're getting their energy from tidal locking, and they're drawing their energy. Rotation is much faster than it should be because it's getting it from the orbit. So I don't know. If you can, I would love to know that paper because I don't. Alpha Centauri is the same age as the sun. You have to be a little careful. Solar stars, people count from F5 to M to K. They call solar. Well, I mean, I don't like that definition.
They claim they were field stars. They were not a member.
Well, how do they know the age? How do they know how old they are?
I don't remember now.
But if you can, I'll be here. I'd like to know that because that's new information for me. It goes against what I believe, but it's good. I'm open mind to have, yeah.
More questions? Suggestions? Okay, so let me remind you that you are all invited to the coffee break that is available upstairs. And let's thank our speaker again.
Thank you.